Hello and welcome to another video. In this video we're going to be working on perfect squares. And in the problem you're given an integer n and you want to return the least number of perfect square numbers that sum up to n. A perfect square is an integer that is a square of an integer. So these are all perfect squares and 3 and 11 are not. So for 12 you want to return 3 because you can get 4 plus 4 plus 4. For 13 you want to get 2 because you can get 4 plus 9. So there's kind of like a few ways to do this. Basically, you can't do a brute force, right? So you need some kind of like n, you can't have an n squared solution, but you can have like an n log n or a n root n, for example. So let's figure out, like, for a number, let's say we have 13. How many perfect squares are there that you can use for 13? Well, you can use like 1, you can use 4, you can use 9, and anything else would be too big, right? Like 16 would be too big. So what we could do is we can like get a data structure of these squares that are up to the number. And the way to do that is you can just iterate from every number to the square root of this number, and then you can do the floor square root. So the square root of this number is going to be like 3 point something. So 3 point something. And we can just round that down to 3. So anything from 1 to 3, the squares are going to be valid. And so what we can do then is we can basically just say, okay, let's just store all of these numbers. Let's store all of these squares. And then for whatever thing we're on, we can try to add all these things. So you can either go down or up. And so I'm kind of show you how to do BFS. So what our strategy is going to be, we're going to start at 0 with 0 numbers. And for every number we have, we're just going to try to add all of these different squares. And we'll also have a visited set to make sure we don't get to the same number multiple times. Because, like, for example, let's say we can get to 4 by adding 1, 1, 1, 1. We can also get to 4 by adding 4. So the fastest way of getting to a number, once we're already there, we don't need to put it in again into our queue, because we would have already got it the fastest way possible. So it's going to walk through like a dry run of this 12 and see what happens. So we're going to have a queue like this. And then basically we're going to pop our item and we're going to have a visited set, like I said. So let's call this V. So because we start with 0, we're going to put 0 in our visited set. And this is going to be like our squares that we're going to be trying to add. So let's actually maybe move it down here. Yeah, we don't even need this anymore, really. So let's move this over here. So this is going to be like our squares that are possible. So we're going to pop this 0, 0, and we're going to check, is this 0, 0? So in this case, we're looking for 12. So we're going to check, is this 0? And the first number is going to be the number, and the second number is going to be like how many numbers total we've used. So is this 0 equal to 12? No, it's not, right? Which means we need to actually try to add all of the squares in our squares as long as they don't make the number too big. So we're going to pop this, we're going to get rid of this. And what are we going to add? We're going to add all of these squares, right? Because we started at 0, so we can add all of these numbers. And how many moves do we have? We have one numbered here. So we can add like 1, we have 1 number, we can add 4, we have 1 number, and we can add 9 with 1 number. So these are our numbers now. And our visited set is going to include these things. So if we get to a 4, a 9, or a 1, like we got to them the fastest way we could. If we get to them again, we don't want to have them again. So our visited set is going to have 0, it's going to have 1, it's going to have 4, it's going to have 9. And then for 1, once again, we're going to do this thing. Is 1 equal to 12? No, it's not. So we get rid of this. And then we see, like, what numbers can we add? Well, we can add all of these numbers, right? These are still going to all be fine. So we're going to add 1 plus 1, which will be 2. And now we have 2 numbers. We can add 1 plus 4, which will be 5. So 5 with 2 numbers, right? 1 and 4. And we can add 1 plus 9, which would be 10. 2 numbers. So this is our queue. And because we're using a queue, notice how like the numbers with the smallest amount, like the sums with the smallest amount of numbers are going to come out first. So that's the whole idea of using a BFS here. And so now we also have 2, we have 5, and we have 10. Okay, so now for 4, we're going to see, is 4 equal to 12? No, it's not. What numbers can we add? Well, we can add the 1, we can add the 4, we can't add the 9 because 4 plus 9 would be too big. So we're never going to add numbers that our result is bigger than this because that's obviously not the answer. So we're going to get rid of this 4, and the numbers we can add is 5, and so we can add 1 to make 5, and we can add 4 to add 8. We already have 5, so we don't need to do that, but we will add the 8. Right, so we will add 8, And we got there in two numbers, right? We added a 4 and then we added a 4. And then we keep going. So for the 9, is that 12? No, it's not. Okay, and then what numbers can we add? We can add the 1 to get 10, but we already have a 10. We also need to add 8 to the visited set, by the way. So we can get 10, but we already have it. We can add a 4, but then we'd get 13, so we don't want to have that. And then we can add a 9, but that would be too big as well. So we can't really add anything for this number. So there's nothing we can add because it's either too big or visited already. Then for this 2, 2, we can add a 1 to get 3. Do we have a 3? No, we don't. We can add a 4 to get 6. We don't have a 6 either. And we can add a 9 to get 11. So we don't have any of those. So we can those are all valid. So we're gonna have 3, 6, and 11, and we're gonna add all those to the queue. So we're gonna move this and add all these numbers to the queue. So 3 with 3 numbers, right? 1, 1, 1. 6 with 3 numbers, 1, 1, 4. And finally, 11 with 1, 1, 9. 11. Then with this 5, 2, we're gonna, and then we need to add all these to the visited. So 3, 6, 11. So you could notice, like, because you have your numbers in your visited, you're never gonna have more than n numbers in your queue total. Because like you're gonna just have visited all of them, right? You can just visit 1 through n, so you're never gonna repeat the same ones. Okay, so for 5, if we pop it, 5 is not 12, so that's not good. But we can add 1 to get 6, but we already have a 6. We can add 4 to get 9. Do we have a 9? Yes, we do right here. And we can also add 9, which would give us 13, which is too big. So we can't add anything, so this is just gone. Then for 10, we can add 1 to get 11. We already have 11. We can add 4, which is 13, too big, and 9, too big as well. So this is gone as well. And then for 8, we can add 1 to get 9. We already have 9. We can add 4 to get 12. And that's yeah, so we can add 4 to get 12. Now you could just end here, but I'm going to put it into the queue. Because you might have a 12, beforehand. So we're going to have a 12. Let me see how many moves. I think it was 3, right? Because we had 8, 2. So now we add 12 to our visited set. So for 3, we can add 1 to get 4. Do we already have a 4? Yes, we do. We can add 4 to get 7. Do we have a 7? Looks like we don't. So we're going to add that. And we can add 9 to get 12. And we already have 12. So you could, like, the first time you reach your number, you could just return right away there. Maybe that'll save you something, I guess. But it's not going to make too much of it. It's basically going to be like one more cycle iteration. So the number we wanted to add was 7 with a number of 4. So we will do that over here. 7 with a number of 4. Okay, now for 6 is not what we want, but we can add, oh, and by the way, so since we added 7, we'll put it into the visited set. So we can add 1 to get 7, we already have 7. We can add 4 to get 10, we already have 10, and 9 would be too big. So this is just no good. Then for 11, it's not 12. We can add 1 to get 12, we already have 12, and then everything else is too big, so no good. And finally, we get to the answer we want, which is 12 with 3. So that's kind of the idea here. By using a visited set, like I said, you will only have n numbers at your queue total, not at one time, just total. And you can just go through all of your square roots, and a little simplification you can make to run this faster is, let's say we have some number, right? Like let's say we have 8. We're going to try all of these squares. And then as soon as one square is too big, because our squares are in increasing order, we can just stop right there. So for example, let's say our number wasn't 12, our number was 10. We could say like, okay, 8 plus 1 is fine, but 8 plus 4 is too big. That means everything after this 4 will be too big because these are going to be increasing. That's kind of the idea, is you just basically use a BFS, and the number that gets you there first, you will just return the number of numbers there was. So you just store a tuple of the number you currently have and how many numbers you've used. And this is a really common pattern, so definitely one to learn. So let's code that up. So essentially, first we're going to make all our squares. So it's just going to be I times I, for I in range. And so the squares we can use, like let's say we have some number, the squares we can use are going to be 1 up to the square root of the number, right? And we can floor divide that. So for example, if our number is like 5, the square root of 5 will be like 2 point something, so we can use 1 and 2 and so on. So this is just going to be the floor divide of, or the floor of this value basically of n to the this, right? So you just take the square root of your number and you you round it down. And you want to do +1 because, like, let's say your number was 4, you would get 2 here, but this number is not included because the range doesn't include the last number, so you do a +1. Then you have a visited set, and like this is very, very common for a BFS problem where you're trying to get from something to something in the least amount of moves possible. So you basically have a visited set, you have a BFS, which is just going to be a deck, and you put in some number with 0 moves typically, so numbers, moves, whatever. So that we're going to start with 0 numbers total, and we're going to add. We don't really need to add the 0 because technically, like, we will never get 0 again. So I guess technically we don't really need to add 0 to the visited because, like, we're only going to be adding numbers that are 1 or bigger, so we're never going to visit it again, so it doesn't really matter. But you could add it as well. I guess we could add it because this is the typical format you'd have. So you have some BFS, and then you visit the number that you started at. And the best way to do these BFSs is you mark things as visited right when you put them into your queue. Because in a BFS, since it's first in, first out, the thing that was in there first will come out first, right? So if something's already in there, you don't need to put it in there again because basically like all your edges, like if you thought about this as a graph, all your edges have 1 weight. Where if, like, let's say you were asked, okay, like I'm trying to get the sum of some numbers, but I have some kind of preference, like these numbers have a weight. Right? Like adding a 4 is like more expensive than adding a 1 and so on. Here, because every number counts as one number, you can think of this as like a graph with length 1 edges. So once something is in the queue, you don't need to add it again because the first, like, because it's first in, first out, the thing that was in there first will come out first always. So that's why you can just add things to the visited set right when you add things to the BFS. But if you use the heap, then you want to add things to the visited set only after you get them out of the heap, because if something is in the heap and you add something else, it doesn't mean that the thing that was in there first is going to come out first because there's weights. So you could say while your BFS has items in it, we're going to pop things, right? So we're going to have a number and we're going to have a moves. So this moves is technically like to the total number of integers that we use to get this. So I usually just call it moves, but you can call it something else because this is a really common pattern. So you pop the number and you check if the number is n, then you return moves, which will be our total like integers that we have. Now we want to go through all of our squares and we want to try to add those things to our number. And we want to keep adding them until we either run out of squares or until that result is too big. And when that result is too big, like I said earlier, because these squares are increasing, if one number is too big, then all the rest will be too big because so we can early break to make it faster. So we can say for square in squares. For one thing, if this result is already visited, we don't need that. So if square plus num in visited, we can continue. Actually, we can do it the other way. We can do this condition first. So if square plus number is greater than n, then every other square will be greater than n, so we can just break here. And if it's visited, we'll continue. So like I said, right when you add things to the queue, you can add to the visited set. So we'll add it here. So visited add square plus number. And in fact, we can probably even make a variable for this, so we can say like total equals this and just use total here. So total, and total. Since we were using the same thing over and over. Now we add it to our queue, so we will append a tuple of the total. And to get this total, we had our previous number of integers that we had, and we added one more, right? So it's going to be moves plus 1. And I believe that's it. So now we just need to have like a default return. I think this will always give you a solution though, because you can always just like keep adding one worst case scenario. But typically you want to have a default return, just like whatever, see if, you know, if you actually, like, let's say you did this wrong, then you would know like, okay, I screwed this up and then it's not returning. But yeah, I think that should be most of it. Let's see if we screw anything up. Okay, looks pretty good. So that's kind of the idea. So some things to think about that makes things faster. Only go through valid squares, right? You can't brute force. We can't try to add every single number. We want to minimize the number of things we check. So we don't want to like brute force 1 through n or something and check if it's a square. Instead, we want to actually pre-compute the like squares possible. Secondly, because our squares are increasing, you know that like if one square is too big, the rest are too big. So this is going to save us time. So notice if we take this out, this should still run. Like if instead we didn't have a break, if we said like continue or something, this is going to be like significantly slower. So that's like another thing. Actually, well, I think it should be in general. I guess it depends on test cases. Anyway, oh, I think maybe it's because no, actually, I did run it. Yeah. So it depends on test cases. Okay, but that is like an optimization you can have. And yeah, the other main thing is add things to your visited set, right? When you add this to the BFS. So this template is pretty much obviously not for this like fair square for square, but this template of making a visited set, making a deck, adding the first number to the deck, and then popping from the BFS. And then as soon as you add things to the BFS, add it to visited, you can use this for a ton of problems. And this is like the most common BFS template. So definitely would recommend this. And like I said, if you use a heap, instead of adding to the visited set here, you can't do that. You would have to add it when you pop. So that's the difference. So in a heap, you can have the same number twice because there's like an edge, there's like a weight property, but here there is no weight property. Every number just counts as one number. So it would speed it up by doing this. Yeah, and I think there are like some other things you can get it down here, but that's kind of like super specific and not super important. I think the main thing is just this. And like I said, you can do this with DP, similar kind of situation. For every number, you figure out like what are all the squares for that number. But I think for a BFS, it's a little bit faster. So you can do either one. And I think the time complexity is going to be a little tricky here. So I guess if you think about it, you can only add so this squares thing is just going to be root n. And then here, I think this is actually going to be strictly O of n, I want to say. But I'm not entirely sure. I think like, because we can only add each number once. Yeah, so the number of numbers in squares is going to be like root n. So this will be root n. But you do have to check if it's in visited and so on. So I think actually it's going to be something like n root n still. Something like this. Because even though a bunch of your numbers can be in visited, you still might have to go through like all your squares just to double check that. I think that seems kind of right to me. It's kind of hard to figure out this exact thing, but I think it's something like this. So I don't think it's going to be strictly O of n. And for the space... So this squares thing is root n, but visited is obviously O of n. So that part's a little bit easier, right? You can only visit each node once. And yeah, it's only have a node in the queue once. So I think it's going to be something like root here. It's actually not really going to be square root. It's going to be like a little bit more complicated, I think, because it depends like how long it takes to get here. So you can think of this as kind of like a tree where you can have like the first level as like 0 moves, the second level is 1 move, 2 move, 3 move, and so on. So it kind of depends on like what are the levels of the tree. So I think it is a little bit complicated, but I think we can leave it something like this. I think it's like reasonable-ish. Yeah. And I think that's going to be all for this one. So if you did like this one, please like the video and please subscribe to the channel. And I'll see you in the next one. Thanks for watching.